pressure, what pressure is, how it comes about, and how we measure it. And as we did with the gases FET yesterday, we're going to start off by defining pressure. And pressure is always going to be given as a force divided by the unit area. And in this equation, we see two things. We see the force and the area in working in opposite directions. So the pressure goes up if either the weight or the total force goes up or the area goes down. And conversely, the pressure will go down if the weight goes down or the area goes up. And you guys have a good intuitive feeling for what pressure is. When you're sitting on your chair, you're exerting a pressure onto the chair, and that pressure is due to both your weight and the surface area of the chair. And the surface area of the chair is usually a nice broad area for you to sit on. And you know that you wouldn't want to turn the chair over and sit on one of the legs only because that surface area is too small. And so the pressure will go up even though your weight is the same. Anybody who's worn high-heeled shoes knows about this as well. Trying to cross grass in high-heeled shoes generally will result in your heel going into the grass, and walking on the flat part of the shoe is what you need to do. And also snowshoes make use of the same effect, where you take the weight of the person, distribute it over a wider area, and then you can stay on top of the snow. So it's really the pressure that's the important thing, not the weight itself. When it comes to gases, the pressure comes from the collisions of gas particles, changing colors, the collisions of the particles. These can be either molecules or atoms with the wall of the container. And that's what we see over here. We see the gas particles colliding with the walls of the container. And as they do, they impart a force onto the wall of the container. And the container has a certain area, length times width times height. The inside the surface area, that's their volume. But inside that length times width times height, you've got the surface area. And that gives you the pressure. We can change the force. Change the pressure by changing the force, and the way you change the force is you change the kinetic energy. Ke stands for kinetic energy, which is really the speed of the particles, and you can change the speed of each individual particle. You can also change the number of particles. So if we increase the number of particles at the same average speed, then we're also going to increase the pressure or change the pressure. And you can also change the area. And changing the area, as we saw in the FET, comes about from change in the volume of the container will change the surface area inside the container. Now, we live in a sea of air, and that sea of air has a pressure. We call that the atmospheric pressure, and you probably hear about this atmospheric pressure in the news. If you watch the weather reports, they talk about the pressure going up or going down, and that has to do with how much water is in the air, making it heavier or lighter. But the atmosphere does have weight. You don't feel that weight because we've evolved in this environment, and the weight that's pushing down is even all the way around us and inside us as well. But for the atmosphere, essentially, we have the gas particles, nitrogen, oxygen, and other things, are pushing down. They're being pulled down by the gravitational force. And this gravity, or this column of air, this blanket of air, extends all the way up to about 100 kilometers up from the surface of the Earth. Now, that sounds like a big distance, but 100 kilometers is basically 60 miles. And what that means is right now where you're sitting, unless you're at the beach right now, you're probably closer to space, which is about 60 miles up, than you are to the beach. Kind of interesting thing to think about, that the atmosphere, and this diagram kind of shows that the atmosphere is very, very, very thin. It's about, if you think about the thickness of an eggshell, it's less, the atmosphere is thinner than the thickness of an eggshell if you blew the earth up, or blew an egg up to the size of the earth. So what happens is this column of air is pulled down. So as we pull this column of air down by gravity, pulling it down, it's exerting a force above us. And that force, in the terms that you've heard about, is about 14.7 pounds over every square inch, pounds per square inch, or PSI. Now, I'm going to use that occasionally throughout this unit just to give you a reference that you may understand, but we're not going to be using PSI as the standard pressure unit here. We have a couple of pressure units we're going to introduce, and the first one is called the kilopascal. The atmospheric pressure. So we're sitting in a sea of 1 atmosphere. There's what exactly, if we're at sea level, there's exactly 1 atmosphere up above us. So from here up to the top is exactly 1 ATM is the abbreviation for atmosphere, and I have that down here. So 1 atmosphere pressure is 14.7 pounds per square inch, and the SI unit for it is 101.3 kilopascals. Now, a pascal, PA, is equal to a Newton, 1 Newton, which you may remember from physical science in middle school, which is essentially a force, remember Newton's laws of force, divided by 1 meter squared. So 1 pascal is 1 Newton. Now, a pound is about, let's see, a kilogram is 10 newtons. So a pound is about 20 newtons, 22 newtons. So you can figure out how many newtons your mass is, your weight is. Newton is a force, so it's a weight. I'm not going to go through that exercise right now. But when we think about the area, we want to think about how much force is applied over that small area. So if we have an area of 1 square inch, so if this is a 1 inch square, this would have 14.7 pounds pushing down on that 1 inch squared. That sounds like it's pretty reasonable. You can handle 14.7 pounds per square inch. It does build up quickly, though. This unit, 101.3 kilopascals. If you convert that to a weight, to a mass, it turns out to be about 10,000 kilograms on every square meter. Now, how big is a square meter? A square meter is about the size of 4 of your student desks put together. All right, so it gives you a visualization for what a square meter is. How about 10,000 kilograms? Well, 10,000 kilograms is about the weight of 3 grown elephants. Can you imagine 3 grown elephants sitting on 4 desks? Of course not, because that's a ridiculously strong force. And that's basically how strong the atmosphere is. So there's a lot of pressure being pulled down on us because the air does have a lot of weight up above us. And we're going to have an article and reading in a little while in which you're actually going to calculate the weight of the atmosphere. It's a lot. You'll be surprised. Now, like I said, we exist, sorry, that wasn't supposed to happen. We exist in a sea of 1 atmosphere. When you go up in elevation, so say you decided to take a trip, or maybe your family moves to Denver. Denver, I'm going to exaggerate here, but Denver is up at about 1 mile high. Now that doesn't seem like a lot, 1/60th of the way up. But the atmosphere is not a linear function. It's a lot heavier, a lot thicker down, denser down near the bottom than it is up at the top. And it falls off what we call exponentially. So Denver, there's less air up above you. So there's less air pushing down on you. So the air pressure is reduced. And the air pressure in Denver is actually relatively low. It's only about 2/3 of an atmosphere. So it does drop off pretty quickly. On top of Mount Everest, it gets down to 1/3 of an atmosphere. And that's why climbers on Mount Everest bring oxygen with them, because the air pressure is just not enough to support them. So just how strong is the atmosphere? We have these devices that are called Magdeburg spheres. And I have these I have a video that I posted along with this to show you how these Magdeburg hemispheres actually work. I have some of these in class, but obviously we don't have them with us, and I don't have a vacuum pump that I can use to demonstrate them. So the Magdeburg hemispheres are two hemispheres of metal that you put together, and when you first put them together, the pressure inside is equal to the pressure outside. And you can see that the arrows, these arrows on the inside and out, are equal length. Those arrows are basically indicating the forces that are being applied. These are like the arrows that you would have drawn on the FET for the syringe on number 7. All right, so this is balanced. And as you saw in the video, these are easy to take apart because the balanced force means that it's the same inside and out. So now we're going to remove the air, hook this up to a vacuum pump, remove the air, and we're going to leave inside a vacuum. VACUUM is how you spell vacuum. What that means is the air pressure inside is now much, much less than the pressure outside. And so the arrows now are not matched up. And it's not balanced, and this becomes very hard to separate. And as the video shows, the two gentlemen trying to separate these had a very hard time. They couldn't take them apart. Now, I've calculated that the area, the surface area of the hemispheres in the video and in lab is about 20 square inches, give or take. This is a rough estimate. And if I multiply that by, again, roughly 15 pounds per square inch, what I end up getting is a force of 300 pounds that you would need to separate the two spheres. And that's a pretty high force that you would need. So just pulling on it like the two men were doing is not going to be enough. Suction cups work the same way. Very inappropriately named suction cups do not suck. As Mr. Lusick would say, nothing sucks. But here's how suction cups, we're going to continue to use the name since that's what you know them by. The way a suction cup works is this. When you first put a suction cup on a surface, the number of gas particles inside is equal to the gas particles outside, and the arrows pushing out are equal to the arrows pushing in. So no net force, and you can put the suction cup down and lift it up however much you like. But then when we push down on the suction cup, what you're doing is you're removing the air. Actually, let me redraw that one. Removing the air. So now there's nothing inside. Inside that, we now have a vacuum. There's nothing pushing out, but the atmosphere is still pushing down. And so the suction cup does not hold onto a wall. The air pressure pushes the suction cup onto the wall. So a little bit different way of thinking about, and that shows you would not work in outer space because there's no pressure pushing down. So that's a little exploration of what pressure is. How do we measure pressure? You may have heard on the news talking about barometric pressure, and we measure pressure using a device called a barometer. And on the right is a diagram showing what an old-fashioned mercury barometer would look like. So we've got mercury liquid here. And in the first diagram, we have an open tube. And since the open tube is open to the air pressure, just like the Magdeburg spheres, is the same inside and out. So there's atmospheric pressure pushing down all the way around, and that pressure gets down into the tube. Now, in part B, we're going to seal the tube off and put a vacuum in here. Now, remember a vacuum, there's no air, no collisions. But pressure needs to equalize. So there's no pressure above the mercury. So let's seal this off. Let's take a look at this left one. Let's seal it off, remove that arrow, and remove this arrow down here. So I can't erase it, but let's pretend that arrow doesn't exist. So now there's no weight, no force. Let's use force rather than weight. No force inside the tube. But pressure needs to equalize. The pressure everywhere needs to equalize. And with a liquid, that liquid can flow and allow the pressure to equalize. So the air pressure is going to push. Air pressure is going to push the liquid up into the tube. This is exactly the way a straw works, by the way, where you're not sucking on the straw. As you inhale, you're basically creating a low pressure region, and the atmospheric pressure outside is what's pushing your soda or your milk up into the straw. All right, so back to the mercury. It turns out that we need to have an equal pressure, so we need something pushing down. So what happens is the mercury rises to this height of 760 millimeters, where at that height, the weight of the mercury is exactly equal to the weight of the atmosphere. Now remember that atmosphere goes all the way up to that 100-kilometer mark. So in just 760 millimeters, less than a meter, the mercury, because it's so dense, and let's write that in here, 760 millimeters of mercury. Mercury is so dense that it has the same weight, 14.7 pounds on every square inch, pushing down on that mercury, or pushing down on the air. So inside and outside have now the same pressure. It is independent of the diameter of the tube, because as the diameter gets bigger, so does the area that you're pushing down on. The weight gets bigger, but the area gets bigger, and those counterbalance each other, and the weight of the diameter of the tube doesn't matter. However, the liquid that's in there does, because the density is going to be different. We could use water in a barometer. Now, they use mercury in old barometers because it's a convenient liquid. It's very dense, and you only have to get to 760 millimeters. Water could be used as well, but because water is 13.6 times less dense, so as the density goes down, the height of the column has to go up. And the water column, you need 10.3 meters, excuse me, or 10,300 millimeters, which is about 3 stories high, to match the same weight as the air above the barometer, or to match the same weight as the 760 millimeters of mercury. The 760 millimeters of mercury is exactly 1 atmosphere of pressure. And we're going to show the equivalence to the other units in a few moments. And since the barometer was invented by an Italian scientist named Torricelli, we're going to take that unit torr, that word torr, and we're going to make 760 millimeters of mercury is equal to 760 torr. They're the same unit. In the lab, we can't use a barometer because barometer needs to be open. Oh, by the way, barometers nowadays are electronic, and your phone actually has a pressure sensor in it. And if you download an app called Barometer Plus, you can actually measure the atmospheric pressure. And I'll be using that in the lab that we do next week when we need to measure the atmospheric pressure. In a laboratory setting, we want to be able to measure the pressure, and so we use a device called a manometer. Manometer. It's measuring manos. I don't know what that means. Manometer. It measures the pressure of a gas in a container. And so we hook up the manometer to the gas through this valve, and the gas pressure pushes down on the mercury. And since there's a vacuum over here, the height of the mercury, the height difference is the pressure of the gas measured in millimeters of the mercury, which you can then convert to any unit you want. Speaking of conversions, we have a little dimensional analysis. Yay, dimensional analysis. All these units are equivalent, and these units are all in chart B. That 1 atmosphere is equal to 760 millimeters of mercury, 760 torr, or 101.3 kilopascal. And you may have to do some converting, so let's see how that works. Each one of those units is equivalent, so you can use any 2 units you need in a conversion factor. So for example, I want to know how many millimeters of mercury could be supported by a pressure of 56.8 kPa. This just means what is the height of the column of mercury that you would get. So I've got my kPa. Let's use this color. We've got my kPa, and I want to then use the 101.3 kPa in the denominator of my conversion factor to cancel out. And I'm then going to take my 760 millimeters of mercury, since that's what I want as my final unit, and put this up here. And this is going to give me my answer. Cancel out the kPa. We left in millimeters of mercury, and that's 426 millimeters of mercury. And that makes sense. 56.8 kilopascals is a little over half of an atmosphere. 426 millimeters of mercury, half an atmosphere would be 380. And so that's just about right. And nice to do a little mental check along the way. Finally, we have this thing called Dalton's laws of partial pressure. What Dalton's laws of partial pressure tell us is that gas particles, since they don't interact with each other, the partial pressure, now the partial pressure is the pressure of a gas if it's alone, we'll just add. So here's how we can demonstrate that the gas particles don't interact. Let's draw a whole bunch of particles, and this could be a relatively small container. And this would be the pressure of gas A, the purple gas, if it was by itself. And let's add to that some more particles, these orange particles. And notice they're pretty far apart from each other. They're not interacting. This would be gas B if it was by itself. And finally, let's go to our light blue again. And again, we can fit those particles in between. And so we're going to add the pressure of gas C if it was by itself. And so the total pressure is just going to be adding them all up. This is really straightforward. Please don't overthink this. You don't have to do any fancy math. It's just adding. So if I start off with a gas sample that has 0.38 atmospheres of nitrogen and 0.24 atmospheres of hydrogen, my total pressure is going to be the pressure of the nitrogen plus the pressure of the hydrogen, and that's going to equal 0.38 atm. Please make sure you put the units in there. 0.24 atm for the hydrogen gas, add it together, and we get 0.62 atmospheres pressure. Okay, relatively straightforward. If we have a mixture and we know what the total pressure is, and we're given the partial pressures of other gases, oh, why did my argon get capitalized there? The total pressure is going to be the pressure of the argon plus the pressure of the neon plus the pressure of the krypton. Now, we want the pressure of the krypton, so we're going to rearrange that, and we're going to say the total pressure, the pressure of the krypton is equal to the total pressure minus the pressure of the argon. Now, you can say minus the pressure of the neon, or we can put them in parentheses and add them up and then subtract them. So the total pressure, 95.4 kPa, subtract off total 25.8 kPa. Oh, sorry, I got those backwards. That's okay. Addition is cumulative, 38 point, or is that right? Cumulative, yeah, 38.9 kPa, and that gives us 31.7 kilopascals as the partial pressure of the krypton gas. All right, so you've got the homework to work on, and please get that done. Don't hesitate to call me if you, or to email me if you have any questions. Thank you. Have a great day.